So our lesson for today is actually what you call this. We'll discuss the Laplace transformation in differential equation. Ayan. So, this is our topic for today, and as you all know, I have already discussed the Laplace transformation, the basic principles, how to Laplace transform functions, and at the same time, I have also discussed in the class the inverse Laplace transform in normal functions of S domain. So we have to revert back the S domain to X domain in mathematical functions or equations. So to appreciate more the Laplace transform, I will be discussing the Laplace transformation in differential equation. Note that the application or basic application of Laplace transform is to shorten the solution of various differential equation. In your differential equation class, you have already learned different types or different approaches in solving differential equations, such as separation of variables, solutions in homogeneous equations, linear equations, the Bernoulli's equation in differential equation, and other things like that. But here, we will be uniformly use the principles of Laplace transformation in differential equation. Note, class, that I have already uploaded my written notes in Laplace transformation in this topic in applying Laplace transformation principles in differential equation. So here I'll be having a recorded lecture on how to solve differential equation using Laplace transformation, so that for a better appreciation and for better understanding of you guys. So before anything else, we have to understand how or what are the things that we should be using in before we solve various differential equations. So the basic principles that we need to understand in this topic are: what is the equivalent Laplace transform of each differential terms? Since we're going to Laplace, or we'll be taking the Laplace transformation of each terms in the differential equations, we need to understand what is the equivalent, or what are the equivalent terms of Laplace transformation in each differential terms. So what I'm referring to is the usual values of the usual values or the usual mathematical phrases that you're going to meet or you're going to solve in each differential equation. So first off is, I have to write this in this manner. We have to note the following. Okay, so first is, we have to understand to get the Laplace transform of a simple function or y. So okay, so in this manner, for a fact that we're dealing with x domains as a function of y, so therefore we'll have a Laplace of function of x. And for a fact that the Laplace of function of x is a function of s, the big letter f, the function of s. Yeah, and that's it. Or for some other textbooks, they use y of s because y can be written as y function of x, diba? Similar with f of x, similar to this one. But here it's f of x. It depends. It's up to you. But for purposes of the lecture, we'll be using y of s because what you usually see in differential equation, it's in terms of y. So if we use y, then we should use also the counterpart of y, which is a big letter y. So therefore, we'll be using this one and this one and this one. Okay. And then getting the Laplace of y prime, or the first derivative, because we're dealing with derivative. I don't know, the right term is the differentials. So the first derivative of y, what is the Laplace transform of the first derivative of y? In this function, we need to understand that this is also equal to f prime of x, which is, we'll write it in terms of y. So the value of first derivative is s y of s minus y of 0. So what does it mean by y of 0? This means that the value of y, or the independent term, if x is equal to 0. So that's a value. Next is the Laplace of y double prime. So we'll be using s y domain, x domain. Y double prime of x equals s squared y of s minus s y of 0 minus y prime of 0. So what does it mean by y prime of 0? That is the value of the first derivative if x equals 0. Okay, let's proceed to the third derivative, y double triple prime. It's f triple prime of x. What is the value of that? S cubed y of s minus s squared y of 0 minus s y prime of 0 minus y double prime of 0. Okay, so let's solve a differential equation. Okay, but before that, I just want to emphasize this thing so that you can still remember. You note that this is a differential of y at the third order, and then you have the third degree, or the degree of s domain is 3. So you match the order with the degree. The order of y in terms of the degree of s cubed. In this example, it's s cubed. Then you have the decreasing power of s. So this is s cubed, then it becomes s squared, and it becomes s, and it becomes s to the 0 or 1. Then you have y of s as a big letter in terms of the function of y function of s, the Laplace equivalent, and then y of 0, y prime of 0, y double prime of 0. So you notice that if the order is at the third order, the order of the differential in terms of 0 will be reduced to n minus 1. So in this case, it's 2. So y double prime 0. So in looking at the second differential, second order derivative, so y double prime, we have s squared as a order. It has to be matched between the order of y and the degree of s. And then since it is the second order, you have to, at the last term, you'll deal with y prime of 0 or n minus 1 order from y double prime. So order of this is 2. You have the power of 2. And then the power, or the order of the derivative of y of 0 is y prime, or first order. So that's it. Okay, remember that. So let's solve an example. So let's have an example. So let's solve y double prime plus y is equal to 0. So if that's the given equation or differential equation, we'll be dealing with general solution. So if it is general solution, the answer to be expected should be in a form of a function with arbitrary constants. So to get a particular solution, that's another type of solution, we have to set limits. So if the function has given limits, we'll be dealing with particular solution. So we have limits, like for example here, y of 0 is equal to 0, y prime of 0 equal to 1. So it means to say that the limits given in the equation is if x is 0, the value of y is 0. If the value of x is 0, the first derivative is 1. So let's apply what we learned a while ago. So for the first example, y double prime plus y equals to 0. So we substitute. Let's use another color. Say blue. So y double prime, the value of y double prime can be found in the equation number 3. So this becomes s squared y of s minus s y of 0. What is y of 0? In the given limit, it's 0 minus 1. Okay? Plus, what is Laplace of y? It's y of s equals to 0. So note class that we are getting the Laplace of each term. Okay? And then, get the value of y of s, retain it on the left side, and the other terms which are not in terms of y of s, such as this one, should be written on the right side of the equation. So we'll transpose 1 from here, negative 1 from here, becomes 1. And then to get the y of s, should be divided by the coefficient of s squared. The coefficient of y of s. The coefficient of y of s here is s squared plus 1. Because the coefficient of y of s here is s squared. And then we're adding it to the coefficient of y of s. It is 1. So when we add s squared plus 1. So that's the coefficient of y of s. So therefore, we will be dividing the coefficient of y of s to get y of s. So that is s squared plus 1. Then we get the inverse Laplace. So what is the inverse Laplace of y of s? Simply y. Alright? And then, the value of this, the inverse Laplace of 1 over s squared plus 1 is similar to the equation of omega over s squared plus omega squared. And the inverse Laplace is sine omega x. In this equation, your omega squared is equal to 1. Therefore, your omega is equal to 1. So, by the value of the inverse Laplace, your value should be written in terms of sine omega x. Since omega is equal to 1, it becomes x. So, simply, the answer is y equals sine x. So, that's the first example. Okay, class, let's try another example. So, for example, y double prime minus 4y prime plus 4y equals to 0. And then let's have another limits. Y of 0 equals to 1. Y prime of 0 is equal to 0. So in this example, let's again take the Laplace of each term. So the Laplace of y double prime is s squared. Okay. That is s squared y of s minus f of 0. F of 0, y of 0 is 1 minus 0. So that is y double prime minus 4y prime. What is the Laplace of y prime? S, y of s minus y of 0, which is 1. So minus 1 plus 4. What is Laplace of y? So it becomes 4y of s equals to 0. So retaining y of s at the left side and all non-y of s can to be transposed at the right side. So it becomes, so what are the what are the terms to be transposed? S, positive 4, and that's it. So it becomes S from negative, positive 4 becomes negative, negative 4, and divide it to the coefficient of y of s. To get the coefficient of y of s, that is s squared minus 4s plus 4. So what is the coefficient? It becomes s squared minus 4s plus 4. Okay? So in this manner, this is a fraction of s term. So, and you know for a fact that the denominator is repeated, this is a repeated factor of s minus 2. This is s minus 2 quantity squared. So therefore we can expound this in terms of fractions, or what they call this in mathematics, it is partial fractions, right? So we designate a over s minus 2 plus bs over, it is b plus b over s minus 2 quantity squared. So that's it. That is the formula for repeated or case number 2. So y of s, then we multiply this equation and this equation by its LCD. What's its LCD? S minus 2 quantity squared. So therefore we can write this as s minus 4 equals a times s minus 2 plus b. Okay, and then let's solve the coefficients. So what's this? So s to the 1, so the coefficient of s to the 1 here at the left side equals 1. So the other side, this is b. Okay, plus b. Yan. At the left side, it's 1. The coefficient of s to the 1 at the left side is 1. On the other side, it's a. So therefore, we have the value of a already. For s to the 0, negative 4, then negative 2a plus b. We know for a fact that negative 2a is where a is 1. So it becomes, it's negative 2, positive 2, magiging negative 2 to, which is equal to b. So we can write y of s as 1 over s minus 2 minus 2 over s minus 2 quantity squared. Then let's inverse Laplace. So therefore the inverse Laplace is y equals, this one is e to the 2x. The next term is what? What's the next term? So minus So how do we inverse Laplace this one? How do we inverse Laplace this one? So to get the inverse Laplace, change the s minus 2 domain to s domain. So that becomes negative 2 over s squared. So what is the inverse Laplace of negative 2 over s squared? So that is negative 2x, right? So minus, So that becomes minus 2x, okay, we'll use the change of domain from s minus a to s. So then, since we change the domain, we use 2x. Ayan. So to check, let's Laplace this term. This becomes y of s alright, y of s equals Laplace of this is 1 over s minus 2. This one is, since may x counterpart, we Laplace the other side. So the Laplace of so we Laplace x first. So negative 2x, the Laplace of that is negative 2 over s squared, and change the s domain to s minus 2 domain. So pretty much the same. Okay, so the answer is y equals e to the 2x minus 2x e to the 2x from the equation y double prime minus 4y prime plus 4y equals to 0. Let's use another example. So for example, y double prime minus y prime, alright, it should be 5y equals to 0. Sorry, I'm thinking out loud for an equation. I have no notes aside in my iPad, so I'm thinking out loud for an equation that I can explain, because I have the goal, or I have to introduce another principle here. So say for example, y of 0 is equal to 1, y prime of 0 equals to 0. So okay, 4 minus 20 negative 16. Ayan. So y plus 5. Okay. So take the Laplace. So let's take the Laplace of this function. S squared y of s minus sy of 0, it's 1. Minus 0. Okay. Minus 2. Okay. This becomes sy of s minus 1 plus 5y of s equals to 0. So y of s is equal to, okay, all non-y of s terms should be transposed to the other side. Positive, negative s, positive 2. So if it is if it is to be transposed to the other side, it should be written as s minus 2. Let's use another pen. S minus 2 over the coefficient of y of s. So what are the coefficient of y of s? S squared minus 2s plus 5. So in writing, so this becomes s squared, okay, minus 2s plus 5. Notice that the denominator is not factorable. So, what are the factors of 5 plus 5 plus 1 that will result to a sum of negative 2? There's none. So, therefore, we have to write this in terms of completing the square. How do we complete the square? So, if you recall your algebra, so this must be s minus 1 quantity squared plus 4, right? And this is s minus 2. If we are going to rewrite this intelligently or strategically, we can write this as s minus 1 over s minus 1 quantity squared plus 4 minus 1 of the same denominator. S minus 1 quantity squared plus 4. Why do I do this? Simply because this is s minus 1 domain and also this is s minus 1 domain. This is similar to sine e to the bx sine omega x or whatever coefficient you'll use. This one is similar to e to the bx cosine omega x. So why do I do this? Because look at the function. This is s minus 1 domain, s minus 1 domain. So you can simply imagine that this is s over s squared plus 4. So what is the inverse Laplace of that? The inverse Laplace of that is simply y equals, we have s over s squared plus 4. What is inverse Laplace of s over s squared plus 4? It becomes cosine 2x. And then since we used the s minus 1 domain, we should write this e to the bx or e to the x minus, so at the other side, we use the sine omega x. But what's lacking here is we have to multiply this by 2 and multiply this by 1/2. Is that clear? What's amazing in iPad is you can erase. Okay, so that's multiplying by 2. I'm sorry. What's amazing is we have to multiply by 2 and divide by 2. Because this represents omega over s squared plus omega squared. So, in that sense, the inverse Laplace is sine omega x, and your omega is sine omega x. Omega is 2x. And then since you change the domain from s minus 1 to s, so we have to write this at e to the x because of s minus 1. And then since we introduce the neutralizing factor, we have to multiply this by 1/2, and that's the answer. So this is similar to what I have discussed in inverse Laplace transform. Right? So probably this is just a recall or your review. Okay. Number 4. So let's introduce another principle. Like for example, y double prime plus 3y prime plus 2. Then let's introduce another function not equal to 0. Say for example, cosine x, where y of 0 is equal to 1, y prime of 0 is equal to 0. So let's answer. So what's the difference in my previous example is we have the introduction of cosine x. In the previous example, the right side is always equal to 0. So the principle behind this is just to Laplace all of the terms. So we have to consistent on our steps. So this becomes s squared y of s minus What's next? S squared y of s minus s plus 3 sy of s minus 1. We know the drill. 2y of s equate to, what is Laplace of cosine x? It's simply s over s squared plus 1. Okay, so let us simplify. So you have y of s equals s over s squared plus 1. Okay, you have to add s and positive 3 here. And divide both sides by the coefficient s squared plus 3s plus 2. So let's simplify. This becomes s, okay, plus s plus 3 multiplied by s squared plus 1 all over s squared plus 1 multiplied by s squared plus 3s plus 2. So let's simplify further. This becomes s cubed plus 3s squared plus 2s plus 3 all over s squared plus 1 will not be multiplying the denominator because it's useless. We just use partial fraction. This is a distinct quadratic. So case 4. Case number 4. In your partial fraction principles in your algebra or integral calculus. So in that sense, we have to equate a over s squared plus 1 plus bs over s squared plus 1, since the denominator or the distinct denominator factor is a quadratic equation or function, plus c over the next term, s squared plus 3s plus 2 plus ds over s squared plus 3s plus 2. So we have to multiply both sides by the LCD of this and LCD of this. So at the left side, we can write s cubed plus 3s squared plus 2s plus 3 equals to a times s squared plus 3s plus 2 plus b s cubed plus 3s squared plus 2s because of the presence of s. We multiply s by the other factor plus c times s squared plus 1 plus d times s cubed plus s. So in this manner, we can use the coefficient analysis. We just write the coefficient of the required. So the highest degree is s cubed. So on the left side, we have 1 because of the coefficient of s cubed. At the left side, it's 1. On the other side, it's just b plus d. So therefore, d equals to 1 minus b. In s squared, we have 3 at the left side, a at the right side, a plus 3b, okay, plus c. So there's no d in s squared. S to the 1, we have 2 at the left side. We have 3a plus 2b plus d. Alright? And we know for a fact that d is equal to 1 minus b. So therefore, by simplifying, we have 1 here and then 3a plus b. Okay? S to the 0. Let's go back. Our constant is 3 at the left side. At the right side, it's 2a plus c. So here, we can write c equals to 3 minus 2a. So from here, we can write additional equation. 3 equals a plus 3b plus c. What is c? 3 minus 2a. So by simplifying, we have 0. Right? Cancel yung 3. Cancel. 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 And then, we have negative a plus 3b. Therefore, a is equal to 3b. And then, based on this equation, we can write 1 equals 3b plus b. So, b is equal to simply 1/4. And by this equation, we can simply conclude that a is 3/4. C is equal to 3 minus 2a. 3 minus 2a. Where a is 3/4. So, it becomes 3 halves. 3 minus 3 halves is 6 halves. Well, actually, 6 halves minus 3 halves. It's 3 halves. And finally, D is equal to 1 minus B. 1 minus B is 1 minus 1/4. It becomes 3/4. So, we have the values for A, B, C, and D. We can write the y of s. Y of s is equal to A over, so it becomes 3/4 times 1 over s squared plus 1. Alright. Plus b plus 1/4 times 1 over s squared plus 1. On the next factor, we should write well, actually, guys, I forgot to introduce that s squared plus 3s plus 2 is factorable. So, well, actually, we just used a wrong approach, but since we can write this s plus 2, s plus 1, so it becomes 3 distinct. So, 1, 2, so it's just a similar approach. Okay, but we just have to redundant some things, right? So, by having C, three halves, 1 over s squared plus 3s plus 2. Okay. Plus 3/4 times s over s squared plus 3s plus 2. Okay. So what to do next? We actually combine this. Sorry, this is a wrong approach, but we will arrive at the same answer. So here we have to get the additional partial fraction. So for the encircled equation, we have to equate this actually in e over s plus 1 plus f over s plus 2. So, emphasizing that this s plus 1 and s plus 2 are distinct factors. So what to do next? E over, so you have to multiply everything by the LCD. So what happens is, we have 3 halves plus 3/4 s equals to E s plus 2 plus f s plus 1. Here, the basic or the most convenient way is to let the other side s equals to 0. the factor of 1 becomes 0. So let's say s is negative 2. So that e would cancel out. So if s is negative 2, 3 halves plus 3 fourths times negative 2, 0 plus negative f. So therefore our f becomes, so what is 3 halves? So we have to cancel this out. This becomes 2. 3 halves minus 3 halves is 0. F is 0. So last 0? Sure? Okay, let's try another example. If s is equal to negative 1, so it becomes 3 halves plus 3 fourths times negative 1 equals E. So therefore E is equal to negative 3 fourths? No. 6 fourths. Yeah, negative 3 fourths. Okay. So if f is 0, 3 halves minus 3. If f is 0 and e is equal to negative 3 fourths, therefore, this whole thing, the encircled one, becomes, what's the value of e? Negative 3 fourths times 1 over s plus 2. Okay? Can't believe it simplified into one term. 3 halves plus 3 fourths s. 3 halves plus 3 fourths s. So okay, so let's write. For as long as you got the principle, I'm okay with that. So y of s is finally 3 fourths times 1 over s squared plus 1 plus 1 fourth. This becomes, it should be s. 1 fourth times s over s squared plus 1 minus 3 fourths times 1 over s plus 2. That's e. S plus 1. Sorry, this becomes 1 should be, because e, at the value of e, 1s plus 1. So by inverse Laplace, y is equal to, what is the inverse Laplace of this? This is cosine, this is sine omega x. So sine x, so just 3 fourths plus 1 fourth. What is Laplace of this? This is simply cosine x minus 3 fourths e to the negative x. So that's the answer. So the principle is, the steps is take the Laplace of each term, then simplify to get y of s in terms of s domain in the form of fraction. Last, take the inverse Laplace. So that's the answer. Okay. So I think that ends my first lecture. See you on my next series of lecture. Bye.